Sorry.
I'm kidding. I'm totally kidding.
Okay.
You're not. I'm messing with you. Hey, thank you, Tracy.
I think I'm good. Hey. All right, let's get started with the next lecture, Light and Radiometry. It's a pleasure to be here this time. I was supposed to be here, and I was for 3 days in 2013, 2023, sorry, and then caught COVID. And so spent 10 days in a dormitory, empty dormitory, trying to recover and sleeping. So I'm so pleased to be here, at least, and join you this time COVID free. So this lecture is all about light and radiometry. Just a bit of the context here. I'm going to cover the light from the sun, some radiometric terminology. Some of this may be basic, setting up spherical coordinates, because the ultimate purpose is to help you understand what I don't have a blank now. It's a solid angle is. Sorry. Go over two of the main radiometric measurements, radiance and irradiance, and give some examples. So I've got a lot of credits here. A lot of this came from different sources, including Colin Resser, Kurt Mobley, a whole bunch of other people on this. So no surprise to everybody. The sun is our source of light. We call it also a point source of light. So remember that. So this is a view from the International Space Station, imaging the sun and the Earth. So what do we know about radiometric, or sorry, electromagnetic emissions, the black body radiation, theory of black body radiation? It says basically any object with a temperature of greater than 0 degrees Kelvin emits electromagnetic radiation. Four main constant laws here. Planck's law, the spectrum of emission depends on the temperature. The Stefan Boltzmann's law, I should be looking here, but I can't read with my glasses. The hotter the object, the more radiant power it emits, and it's proportional to the T to the fourth power. Wien's displacement law, the hotter the object, the shorter the wavelength of light of maximum emission. So this is basically what the black body radiation looks like, with an overlay of where the visible spectrum is. So our sun basically is running about 5,700 Kelvin, so it emits a spectrum of EMR that is in this maximal range of wavelengths. So now let's look through three different places here. One, that same image, basically looking up top of the atmosphere, above the Earth's atmosphere, staring out at the sun, and as well as capturing the Earth. Now, if we stand on the Earth, we look up. You all do this all the time. Now we see something different. And now all of a sudden, if we're diving under the ocean in the middle of the day and we look up, now you see something different even again. Why am I going through all this? It's just to give you some context. So here is, we'll get to this in a minute, the radiance on the y-axis, wavelength on the x-axis, going through those three different locations. Top of the atmosphere, black line, at the surface of the Earth, the red line, and beneath the ocean surface. So what you notice at the top of the atmosphere, here's the spectrum, lots of little tiny bumps and wiggles. So these are called Fraunhofer lines. They basically are the absorption of gases in the sun's photosphere. And that's where they're caused, by these little, very, very tiny dips in the spectrum. At the Earth's surface, now what do we have? We have the atmosphere of the Earth. So that's the red line. And now all of a sudden you start to see not only some impartation of those Fraunhofer lines, but also some more lines, deep dips in the spectrum. So those are caused by the absorption by gases that are actually in the atmosphere, Earth's atmosphere, into oxygens, water, carbon dioxide, species like that. And so these all come as a very narrow band spectral lines again. And now as you go beneath the ocean, what is happening in the ocean? You just heard probably all last week about this. Water, there's particulates, there's dissolved organic materials, all these then do absorption and scattering. So you got three different spectrums here. I have this slide only in here just to remind you that there's different ways to slice and dice the spectrum. So for in ocean optics, optical radiometry most often refers to the UV, the visible, the near IR spectrums. However, there's a lot of potential to use some of the shortwave SWIR bands to actually understand more about the atmosphere itself as well. Okay, so let's jump into these radiometric quantities. So radiometry is a measurement of physical quantities like radiance and irradiance performed through light measuring instruments called radiometers. So let's just start at some of the definitions. You start with radiant energy. It's got the unit of joule. You move into the radiant flux, which is the energy per unit time. So now we have watts as the measurement quantity. Irradiance, which now is the radiant flux incident on a surface. So now we're taking a surface into account as an area as part of the irradiance measurement. So now we have watts per meter squared. And then radiance, which is the radiant flux per solid angle per unit projected area. So now what we did do is now we look at just a small spot in the sky, a solid angle, or somewhere else, a projected surface, and that gives us the radiance measurement. There's a whole bunch of other things we're going to get into tomorrow called apparent optical properties. We'll talk about these in more detail tomorrow in the lecture. Radiance reflectance, remote sensing reflectance, Q factors, average cosines. All of those are very helpful to us, and we'll get into that tomorrow, but we need to make sure we understand and start at irradiance and radiance measurements. Oh, also note, we do this all as a function of wavelength, obviously. So it could be a big broad band, or it could be a very narrow spectral band in the spectrum. So just a quick review. Like I said, these are a few slides to get you to understand the concept of solid angle and why it's very important in the measurement of radiance and irradiance. So we set up the 2D geometry view. So we've got this circle here on an XY plane. We measure a zenith angle, theta, that comes off of the Y plane. And if we want to measure an arc length, the arc length is then the small change in theta at a distance of radius r. So the arc length is equal to r times the change in theta, d theta. So now let's move into the 3D geometry view. So now we've added another plane, a z plane. And we still have our xy planes. So typically when we think about this, just the z plane is usually you're standing on the earth looking up. XY planes and the rotation of the XY plane, now we add in another angle, P, here to define what the angle is. Basically, in this case, it's usually setting it up with the north plane and the rotation from the north plane. So using geometry again, you can then look at trying to project into the z-axis. How do you define where you are on this point in space here on the z-axis, and that's r times cosine of theta. So you can define all this by geometry, hypotenuse, opposite adjacent of right angles. All right. So now we set up more complex variables here because now we really wanted to understand where we are exactly on that sphere. So we just went over how to do it with z equals r times cosine of theta, using that same logic here and setting up your geometry. You can then define the position, the y position as r times sine theta, r times sine theta sine phi, and x is equal to r times sine theta cosine phi. I get my tongue tied every time I try to do that. Phi. All right, so finally, solid angle. So now we do that same sort of thing. We want to know over a small change in theta and a small change in phi, where are we on that sphere? What space are we mapping out? So here's what we're trying to get at. Small change in phi, small change in theta. So now we define that and define what that surface area is, that shape. And that is equal to r times d theta times r times d theta. Sorry. Man, every time I do this, r times d theta times r times sine theta d phi. Say that 3 times fast. So now we know what that surface area is. Now we just need to know the normalization by the distance away. So that's where this is. The solid angle is equal to the change in the surface area times or divided by r squared. The r squareds cancel out, and it just simply becomes sine theta, d theta, d phi. So does that make sense? I want to make sure you understand solid angle in the definition. So again, if I'm, for example, sitting at the Earth and I look out, I always like to do this sort of like as a Gershon tube. We'll get to in a minute, but I take a paper towel roll, the inside of it, put it up to my eye. I'm making this a really bastardized radiant sensor. But we're looking out then, if I look into the sky, I'm looking at some projected area out in space or some distance away from me. So maybe I want to get up to, I don't know, the middle of the atmosphere. So that's my distance from my point to the atmosphere. But that's what I'm looking at, is that space in that sphere. And that is called solid angle. So let's make it even more complicated. Because first, like I said, normally you'll zenith. Zenith is relative to again, you're upward looking. If you're standing on the Earth, that's the angle straight down. Zenith angle comes off from that straight down. Sometimes you'll hear nadir angle, which is really confusing, which means you're standing up and looking down, straight down at the Earth. So you've got another angle there. It's called nadir. Then all of a sudden now, let's say we're trying to trace in remote sensing where the sun is. We need to know where the sun is. We need to know what angle I'm looking at. So we have more and more complication here, and that now we've got to say, okay, maybe here's my north direction. I know my rotation around the axis is in terms of azimuth, and now I know where I am in zenith, but now I need to know also where the sun is. Because when we do remote sensing, it goes from the sun down to the Earth, through the or down to the Earth's top of the Earth's atmosphere, through the atmosphere, into the water. Some of that light gets reflected out, back through the air sea surface, back through the atmosphere, and now it hits the satellite. So it gets more complicated here, but remember, it's often in literature where you read through literature, some of these angles and the name of the angles and how they're defined will change. Sometimes the sun zenith angle is defined differently or captured differently. The view angle, where you're looking to, and the azimuth difference. Sometimes these denotions change a little bit in these, so pay attention to the actual definitions. So does that make sense at this point? Again, I just laid out here saying, here it is the sun, goes through the surface ocean, some of that light comes back up and then hits our satellite. So you have to trace all those coordinate systems in order to do really, really effective radiative transfer. All right, so let's dig into the actual measurement. Radiance, denoted as L, is the fundamental quantity for all the radiative transfer. It is again defined as the radiant flux in a given direction per solid angle per unit projection area. So typically you'll see a lot of different units. I've got a cheat sheet at the end if I have a little extra time where I can lead you to go find a cheat sheet on how to convert all these units that are you can mess with here in terms of the actual quantities of the units, but typically for most of the radiometers I've used, we measure in watts per meter squared per steradian per nanometer. Again, this is the key quantity that appears in the radiative transfer equation, and this is it. Radiance. What do you see here? Nope, radiance. What do you see here? Yep. And what do you see here? Yep. So there's your connection in a really rough sense. Radiance is directly connected to the full scattering function, volume scattering function, and the beam attenuation. Okay, one good rule of thumb to remember also, what's called the invariance of radiance, or the principle of radiance invariance, which basically means that radiance is independent of distance along a line of sight when you're in a transparent and unchanging optical medium. So in other words, there's no change in the index of refraction of the medium. There's a definition here of how you go through that, but basically it's saying if I've got radiance coming in this direction, and I look back at this direction, it's the same no matter what. The same radiance is being transmitted across a line of sight. So that's the principle of a radiance invariance. It's good to keep in mind so that you don't have to do corrections downstream when you're trying to do calibrations. And I'll show you that on Friday's lecture too. So how do we measure radiance? Again, there's the radiance definition. So I said a Gershon tube already. It's basically a tube that has a slight opening here at the end of the tube. And then it has baffles downstream to try to keep that light collimated or make it more collimated. Then it can't hit a polarizer, depolarizer. It can hit a series of filters, basically, whether they're discrete filters, broadband filters. You can pick your choice there. Then it goes through a diffuser, and it helps diffuse back the light again, and it hits. Key point is we use like a Gershon tube to do that collimation, and then we also use it to produce well-collimated light.
In between the diffuser and the detector, the diffuser is not doing any focusing onto the detector. Is it just equally dispersing the light within that section? So what happens?
Correct. We're just trying to get out of any variations in the light hitting that detector, so that if there's any spatial sensitivity of the actual detector, we're not pointing different light, and we're watching just basically a little beam steering on that. So we diffuse it slightly just to make sure it hits that detector. Doesn't really have a radial distribution in that small cone of light that we're detecting. All right. So again, we'll get to the type of sensors later, but just a quick example of what radiance, spectral radiance looks like. This is for the radiance coming out of the ocean, upweld radiance. So here's sort of the value of upweld radiance, spectral, and then you can't see it, it's blowing up, but basically you're going up, right above the water surface down through different layers, different depths in the water surface. So what are some other things you notice right off the bat in this figure?
Longer wavelengths are attenuated more than the shorter wavelengths.
And this is yet sort of a concentration of 0.25 micrograms per liter. So you can see in the upwell gradients, a little bump there in the upwell gradient. You can also see that the radiance is decreasing with depth. Why does the radiance decrease with depth? What's that? Combined properties of scattering and beam attenuation. So that's beam absorption's losing that light. The scattering is redirecting it. So with different realizations in depth, give you a little bit more context on what the IOPs could look like at those depths. Same thing here. We notice five different channels of radiance with depth. Now just plotted as a function of depth. So 340 is in this purple, 412 is in this weird mauve line, and then 443 is in the blue, green 555, red 665. So what can we infer from this? These are basically just line slices across these. So you can see, again, the impact of the IOPs on the actual value of gradients. Okay, we'll get into more definitions of sort of measurements. You can also measure what's called hemispherical radiance using a camera called a fisheye lens camera, which is incredibly complex to produce. It has some very high twitch optics. It can do it spectrally and then also do it spatially, basically. Spread out that light and then take an image of that light through this fisheye lens. So there's the little lens, it's got a lot of trick optics. It's getting, again, simultaneous radiances in all directions of one hemisphere at several different wavelengths at once. Not many of these have been created because they will blow your $2 million budget right away trying to grade this. So I wanted to put this up to give you a context here. So here, this comes from South Atlantic, Marlon Lewis in Dalhousie. From a long time ago, working with Ken Boss on some of this. Now we have an allotropic environment, Hawaii, with very clear sky atmosphere, and then we have a eutrophic environment, Medford Basin, Nova Scotia, with similarly clear. So now what we have is a color bar that denotes the actual radiance values, low to high, purple to red, and then we've got slices at every 10 meters of that hemispherical radiance. So again, this is all this fisheye is doing in an instant. It's taking my little paper towel tube and scanning it over, 180 degrees all the way around, and as smooth. It does that instantaneously. So I've got the downwelling radiance plotted here, they do, and the upwelling radiance here, both sides. So what do you infer from this? What can you infer from the clear sky case in Hawaii? Where's the brightest part in the surface?
It's lots of direct radiance,
And what causes that direct radiance?
less diffusion because it's clear water. So we can still see diffusion, but yeah.
What is that point?
Oh, this is the upwelling radiance, right?
Yeah.
The sun.
Sorry, this is downwelling
Oh,
radiance.
Germany.
Correct, the sun. That point is where the sun is in that hemisphere. That's the brightest point. I'm scanning around, I'm looking at the sky mostly, and boom, I hit the sun. It's a little bit of an albedo here, probably from some atmospheric and some process of getting that light through the air-sea surface. The transmittance through that air-sea surface. And as you go down, what else do you see?
Decrease.
You see a whole lot of shift in where the sun is?
No.
That's no more contribution of diffuse.
Right, and so we're in Hawaii, very, very clear blue waters. So there's not a whole lot of scattering going on other than by the scattering of pure water. And probably very, very low concentrations of particles. So what we're kind of just looking at here is really the impacts of the absorption by pure water at this wavelength, which really doesn't matter, but mostly the scattering by pure water in the environment. Now what happens when we start looking at upweld? Can you see the sun again? Remember, upweld light, the radiometer is looking down. So we still had some pretty bright light. We could still see the sun down here and our downwelling looking up in the sky at 48 meters, but it's still pretty bright. So that infers that the actual depth of the light penetration is much, much deeper in a clear water environment. But here at 48 meters, now we're looking down. We're going to get to this in a minute. We're going to get this on. I can't remember if it's in a minute or on tomorrow's lecture. Basically, what you're looking at down here is if you keep going down on the water column in a very clear water case, eventually all that light is going to get scattered uniformly in every direction down deep. And so when then you're looking down deep, you're seeing what's mostly the impact of what's called an asymptotic light field, where everything is scattered equally in every directions. And so basically now what you're looking at is a very, you do more depth integration or 48 meters down, 10 meters all the way down to the surface. So you can start to see it's more diffuse, but it's brighter. So that's pretty interesting. But now as we go over to the euphotic environment, here's the depth. So we've got higher concentrations of particles, absorbing particulates, scattering materials, all kinds of things. So what do you see in this image, set of images? Can't really see the sun very well anymore, right? Looks very diffuse kind of as you go deeper and deeper. There's not a whole lot. I mean, the radiance distribution is maybe there's a center there over the outer edge, very high angles. But now, this is only down to 15 meters, by the way. But now when you look back up, a little lower, kind of odd on the edges. So you're looking at the light coming out. So again, what we're going to get to in the irradiance definition is basically how do you get to an irradiance if you have to integrate over all this different hemispheric angles? 180 in the X, 180 in the Y direction. That's a hemisphere. And that is how you derive irradiance. Okay. Wasn't sure if this is the best place to put it in today's or tomorrow's lecture, but there is another law of irradiance called the nu squared or n squared law of irradiance. And it's based on Snell's law, which is basically you got a median index refraction 1. We're looking at a sine angle of theta 1. You're going across from one medium to another, and on the other medium, you've got a different index of refraction in two. And that comes out at a different angle. So that's just Snell's law, how you get through transmission through two different index of refractions. It's more of a broader definition for a light beam crossing the interface between two media with two different refractive indices. The ratio of the radiance to the square of the refractive index of the medium remains invariant when ignoring any reflective losses between these two surfaces. But note, when you change in this across it, two things happen. One, you get a change in both the angle and the solid angle. So one looking this way, starting from this point, starts going that way out, one going down, so you get two different change in both the sine and the angle, as well as the actual solid angle. Yeah.
So on that last slide, when we had that, let's say H2 water, the water with scatterers. In the upwelling radiance, it looks like it's brighter on the edges. But earlier this class, we had learned that kind of if you're a scuba diver looking up, you expect it to be darker on the edges. So what's the intuition behind that switch?
You mean here?
In the eutrophic environment.
Close to the surface.
Meters.
Yeah, you see how it's like brighter on the edges than it is in the center.
Is it corrected for self-shading?
I don't know if it could be self-shading there, but I don't know if that's it. Remember, we're looking down in the ocean coming back up. Right, so we haven't hit the air-sea interface.
Yes, as long as the outgoing light, right, so you're looking down.
Yeah.
And so all that's, the stuff's really diffused, right, so stuff's going scattering in at the sides, so down below you, there's not much light.
Gotcha.
Whereas you do still see that kind of Snell cone, right, in the downwelling light, which is
That makes sense. Thank you.
All right, so that was the spin through radiance. Now we'll get into irradiance. Very useful and common measurement. It's one of the most commonly made measurements in the ocean, in all of ocean optics. There's several different ways to measure radiance. We're going to get to these definitions: spectral, plane irradiance, scalar radiance, vector radiance, and far. These are some more of those. You can define those as an example. Spectral plane irradiance, you can break into the same upward and downward frames. Scalar, you can do the same way, upward and downward frames. Vector we'll get to. It's basically, we're going to show this is what it is. It's basically the vector of difference between the upwelling, downwelling and the upwelling irradiance. So why do we make the irradiance measurements? It helps us to normalize with these irradiance measure, normalize it to the illumination conditions. So in other words, if you've all seen this, you're out in the sunny, it's bright, all of a sudden a cloud passes by, you've got a radiometer there that's measuring upwelled light. You need to normalize it by the actual light impinging at that point in time down on the surface as well. So it's a normalizing factor. It's a good measure of light available to phytoplankton for photosynthesis, whether it's a PAR integration or not. And we also use these measurements to drive various different optical properties and also use to drive through those AOPs and infer IOPs. So the inverse square law of irradiance in this definition, the important takeaway point from this slide is that, again, in a constant media, irradiance from an ideal point source falls off as 1 over r squared. In other words, by distance from my point source. So in this case, as you move further and further away from the point source, it's getting dimmer and dimmer from that point source. It's decreasing by my distance from that point source. So let's jump into spectral plane irradiance, often just called plane irradiance. So in this case, we're going to start with this downwelling. So basically, we're just looking at the downwelling light on the surface. So here we are again in terms of the integration, there's the radiance. So by the cosine theta, sine theta, d theta, d phi again, just like we had before. How do we measure it in reality? Here's the setup here. There's two different versions here. What we have here is the top of the surface, and then we have what's called a diffuser here to make sure, again, the light force is diffuse coming in. That can go through a series of filters and then hit a detector. Notice that most of the radiometers, we have to get rid of some edge effects, out of band stuff coming from different steep angles. So we have put them in a little shallow well with some sort of baffles on the edge, some little keep them all into the measuring into the downwelling plane, the filter and detector. Now, the important part of this diffuser is it has to match what's called a cosine response. So let's get into what a cosine response is. So now imagine, here's my flat surface, my disk, my diffuser disk. If I look straight down it, it looks like a circle, right? So in this sense, and we're setting up our plane here, I'm measuring at a cosine angle of 0. So the cosine should be 1 there. Now I go off at a 45-degree angle and look at that disk. It's a little more oblated, slightly changed in the shape. That's because now I've got the 45-degree angle. Take the cosine of that 45-degree angle, we need 707. And now if I come at a really, really steep angle, I'm just barely looking at the top of that surface. It appears like a disc more than anything, or just a line. So that's because as it approaches 90 degrees, you take the cosine of 90 degrees, the response should be 0 in that detector or that cosine collector. So all good radiometer or irradiance sensors really need a good cosine collector, at least in this planar setup here. So this is basically some graphs and trying to measure how you would look at the cosine response. But here's the cosine in black, kind of imparted on it. This is the degree of angle of incidence, sort of a normalized response. There's that cosine coming in, it's cosine response. And then we make a whole bunch of measurements at very different angles to try to measure what the actual cosine response is in the diffuser. So if you do the difference between, here we go, in angle and degree, and sort of the variation response. So we get out at sharp angles, it becomes really weird. Get out at 60-degree angles, very weird, but at least over somewhere around 45 degrees plus or minus 0, cosine response is pretty small. So you really want to have a good cosine response in your planar measurement, planar radiance measurement. Otherwise, you're inducing error and missing parts or adding in more different parts of the light at these steep angles. Yeah.
So does that mean like you need to manufacture, you have to manufacture your diffuser to a certain size? Like, is that where you're?
Thickness is part of it. The actual index of refraction is a good part of it as well. How you do that. The homogeneity of the material is a big part of it as well. Cosine collectors are not easy always to make, especially when you want to put it in the ocean in terms of finding the combination of materials. There's different ways around that in terms of optically, how you make some adjustments inside, put in more kind of collectors that have different angles or materials at different angles that help collect from that diffuser well to kind of smooth it out a little bit. But yeah, that's, I think I answered your question. Yeah. So lots of time they're made out of Teflon, acrylic diffusers, there's all kinds of different materials to do.
Is this diffuser design also shared with the ACS, with the HU? Does that matter as much? Or is it
Not really, not as much.
because the angles aren't
Yeah.
as sharp?
That and the diffuser in the ACS is fine. It never touches the environment. It's touching the glass. It's not exposed to the environment. So you also want to have a material that is pretty robust to last in the environment. Doesn't age very much. It doesn't lessen likely to get immediate fouling. So you're trying to optimize a bunch of things when you make a cosine collector, particularly one that goes into the ocean. And so that is why, it was a good question. Many manufacturers use different cosine collectors, whether you're measuring in air or water, because you're trying to optimize cosine response for that in media you're in, but you're also trying to use that diffuser as an element that can survive pressure changes, you profile all these things. So this is the word of caution here. When you buy a radiant sensor, like from Seabird Scientific, you must specify whether you want to use it in air or in water. Because the cosine collector will change. So think about that as I have to choose my index for refraction to order the instrument. Let's move on to spectral vector irradiance. So now we just talked about the downwelling irradiance, radiance coming down. The upwell irradiance, E's, is the light coming, the irradiance coming up. Vector irradiance is simply the difference between how much light's coming down at one surface and how much light's coming up. The difference between those two planar irradiance measures. It's often also described as the net downward irradiance. You're just trying to see how much downward light is coming and what that change is like over the ocean, because it is also a very effective parameter at getting to an IOP. So if you look at the change in the vector irradiance over depth, it is equal to negative the absorption at that depth times the scalar irradiance. We're going to get to scalar irradiance in a minute. So it is often can be used if you do this and set up your configuration right. It can be a way to validate or double check or estimate the absorption. All right, now we move to scalar irradiance. So now we're not as worried about cosine collection. What we actually want to do is try to measure more of a spherical measurement. So think about this. Now we've got this sort of huge diffuser. It's like a ball, circle, mounted on a little stock here. And then we look inside of this little ball. We try to collect all the light coming into it, got a filter and a detector. So basically we taken our diffuser and made it a circle instead. So that's the scalar irradiance. So if you put a little absorbing shield right there, put this little block on top of it. So you're trying to block out anything from in this case, this would be the downwelling scalar. we're trying to block out light coming from the upwelling scalar portion. So you get the downwelling scalar portion. If you flip that your sensor upside down, what do you measure? The upwelling scalar radiance. All right. And in this sense, if you think about it now, we're kind of doing the two halves. So the scalar radiance is now becomes the addition of the downwelling and the upwelling two portions of the upper radiance, scalar radiance. The idea is the collection of light to a single point, regardless of direction or angle. That's what we're trying to measure. Thus, it becomes independent of actually the light direction. The detector has the same effective variance of radiances in 80 down direction. Thus, this is why we don't have a cosine factor on them. This is a very good relevant measurement for photosynthesis, as well as also looking at the heating of the water, what's going on in the heating of the water, how much heat is coming in. So now, again, instead of just looking at the plane irradiance, light coming down the plane, now we're trying to look at the spherical radiance in that upward and a downward direction. And that's that EO value appears here in Gerson's law. All right, so R, photosynthetically available radiation, basically the interval from about 400 to 700 nanometers of that scalar radiance times wavelength over HC times the change in wavelength. Now, just like we did in EO, but now we try to not block it, try to make it as small of a little cone or a ping pong ball, with hopefully not blocking too much of that one stock point where we have to make a measurement. So it just becomes now using that measurement to try to understand how do we get to power. Typically uses a scalar radiance design that you can get to it to a plane irradiance measurements, but you have to do a little bit of assumptions on how much light you're losing if you only measure it in one direction. How much of that actual radiance you're losing by doing it at home setup. Typically used in a lot of simple models of phytoplankton growth. It's also used, some ecosystem models use spectral scalar radiance measurements to look at the phytoplankton pigment composition. All right, so way I think about breaking down in this, and you've seen it when you go to probably websites, there's different ways to break down your sensors into different models and characteristics. One we just talked about, you can buy a PAR sensor, whether it's scalar or planar. Two, you can buy different multi-channel discrete wavelength sensors, somewhere between 4 and 19 different, individual 10 nanometer bands. A lot easier to do this because you're using a photodiode in that instead of an expensive spectrometer, which I'll get to. And hyperspectral instruments, right? You're trying to make the continuous measurement over the spectrum, usually at 1 to 10 nanometer intervals, but you're trying to make that realization at one point in time. The narrowband and these multi-band channel instruments here, you've got wavelength, you've got a response function, basically. So they discretize these in different filter sets. 7 different channels shown here. Basically, you're just looking at the 10 nanometer band of light in your measurement. And that could be in irradiance or radiance. You have to be, but actually go on to that. Typically, historically, as ocean color remote sensing came about, more in-water radiometers became available. It was often trying to pair some of the channels, these multispectral channels, with what channels were being measured from a ocean color satellite. So they tried to mix and match them for like a multi-band a sensor like Veers or Modus trying to pick the same channels to measure. Typically, these are a lot cheaper than hyperspectral measurements as well. You have to kind of be careful though, because you have to look at some out of band response things like coming from different parts of, you're letting in light from different parts of the region that you don't want to measure from what the filter set is. They typically, these type of sensors have pretty low out of band effects. But they really do depend on sort of the filter set you're using. So you have to then, instead of tracing one piece of equipment, we'll get to in a spectrometer, you have to now characterize 9 individual unique channels. Each of those 9 channels has its own filter, has its own photodiode. So it's can become a little more challenging to not necessarily track the drift, but some channels might drift faster than others. So I've been mentioning this hyperspectral measurements. Again, continuous spectrum measurements, usually 350 to 1,000 nanometer. It's typically where you can buy an off-the-shelf what's called a spectrometer. These small spectrometers take in light through a slit, a whole bunch of dispersive elements, and then map them onto like a CCD array or a CMOS array that can split that light out into the spectrum components. Their demanding instrument characterizations are needed for these, particularly as you go shorter and shorter wavelengths. You have to really be good. You have to really understand how well your spectrometer is working, and in terms of like your delta spacing. So I've got one channel here, next channel here, 100 of those in a row. You want to make sure you don't have bleed over from one channel to the next in that spectrometer. You want to make sure that delta channel is the same as best as you can over the whole spectrum you're measuring. So there's a lot more characterizations you have to do for these type of hyperspectral instruments. Great thing about these, we talked about way back when in terms of Fraunhofer lines. If you remember that graph, even at the top above, looking at the actual sky that I showed you. If you looked at, remember that plots that I showed you there, you can actually pick up things like Fraunhofer lines. These atmospheric bands and these photosphere bands, they don't really change that much. They can be used for good calibration points or verification points for your spectral resolution and accuracy. So here's a couple plots. This is an LU upweld radiance version here, about 300. I think the 800, this is actually off the HyperNav unit, the project I work on now. That's the SVC calibration for PACE, and it's got about a 2 nanometer spectral resolution. So that system collects 2,048 spectral points each time it measures. Here's a different version of radiant sensor. It's over 10 nanometer, and then you can overlay the bands from either a satellite or a multispectral one. So you can see the difference between the two spectrums and what you're realizing. Get really small scale stuff. You can see things like Fraunhofer lines. You can actually start seeing really definitive causes for these peaks and valleys. They could be atmospheric induced, but they could also be, you're looking for changes in the absorption spectrum as well. The other nice thing about going to a very fine scale spectral resolution is now if your satellite's measuring every 5 to 10 nanometers, like PACE, now I've got the ability to say I'm measuring it at very much lower or half the bandwidth or band spacing. So now I can use that data to try to understand how the satellite's reacting and help characterize that satellite in terms of how it's looking in terms of its bandwidth spacing as well. All right. Probably seen some of these. If not, These are some examples of the multi-channel sensors for both irradiance and radiance. What is this? Yeah. Yes, cosine collector, correct. So that's that element of the cosine collector that is trying to measure a cosine response of the planar irradiance. This is a blurry picture. This is a little bit better. So now we have radiance. Here in the radiance, we actually have a glass window on top of it. What are each of these elements? Dark. You can't see them very well. How do we measure radiance? What are these things called in here?
Oh, the angle.
Gershon tubes. That's your cone. It's your little cone. Or your little paper towel tube. So each of those is the Gershon tube with the filter set and everything behind it. All right, so some example of hyperspectral radiometers, irradiance and irradiance, both kind of combined here. What's that?
Pictures here.
What's that? What did you say?
No, sorry, I was saying the name of the instrument.
Oh, no, what is this little white thing? And yes, okay, that's how you identify them. I thought I learned white irradiance. Glass with a hole in it.
So the
Radiance.
tube only is measuring one angle.
It's measuring one solid angle, basically, yeah.
And like the one that you showed on the slide before where it seemed to have a bunch of tubes, is that all the same?
Those are all different spectral. These are all different spectralizations. So this is one channel, one spectral channel, another spectral channel, another spectral channel, another spectral channel.
And for the radiance, the same?
For the irradiance, the same. These are all, and this is like really multi-huge one, but this is, I think, a 7-channel one. So you can have 7 of those. And behind them is a filter. Through that tube is a filter that's a discrete filter that does this. Here's your channels. Yep.
When we're thinking about the Gershon tube, it's just about the collimation being part, not about the optics between, for example, a multispectral or hyperspectral sensor. Both use Gershon tubes.
Yeah, yes.
Okay.
Yep. All right, let me get back to that. So there's various different manufacturers. Again, these have been around a long time. Oh, actually, I wanted to go back to that because I forgot to say that. You were asking me a good question here about cosine collectors. These all look the same?
No.
Yeah. So when we're trying to do this spectrally, and you've got one material like Teflon, you have to exactly know what the absorption properties of that Teflon is spectrally. And in some bands, that Teflon might not work. It's blocking too much of the light. Again, that's why some of these look very different in color. Is because sort of the material choice has to be tailored to make sure you're getting enough responsivity through that light passing through that cosine collector to hit your detector.
So what's that more clear one then? Is that?
I don't remember the composition of it, or you're asking?
I was wondering, is that like the more like low wavelength channel, like the
Yeah.
UV one, the clear one there?
Yes, this is more like the UV one, sir. I
Okay.
thought you were mentioning, I don't remember exactly the composition of every. I think there's 7 different discrete cosine collectors that we had at Seabird when I was there. That all match different channels. Oop. So, different ways, different platforms. Here's HyperPro series system with a downwelling or planar irradiance, and an upwell planar irradiance as well. So that can give you what is this trying to measure? This is planar radiance in the upwelling direction, planar radiance in the downwelling direction. Quiz again. Why would you want to make that measurement?
The spectral vector rating,
Correct. And that's related to
the difference between those two.
the difference between the derivative of the difference between those two is times the scalar irradiance. So that's why you want to make this measurement is another way to derive. So there's a lot of other Twitch ways optics to do this. Again, this is what I work on. This is the platform. Kind of looks like a hyperpro profiler, except in this case, I've got dual spectrometers and dual radiance, upweld radiance measurements on it. We'll get into more, I think, on Friday of this. We'll go over more of what HyperNav does and Mobi does, but Mobi's pretty trick system as well in terms of the way they set up the optics. Big fiber optic set up on the Mobi system to measure the spectral irradiance at a very high spectral resolution. So just some examples that you'll see out in the field in commercial or in some up and coming or very minimally used type configurations. All right, examples of broadband sensors. So what is this one?
Cosine.
Pardon?
Cosine response.
What is it?
What's a stellar response?
What's that?
Scalar.
Scalar irradiance. It's measuring scalar irradiance. Yep. What's this one measuring?
No, it's my accent, it's terrible. Sorry.
No, I can't hear sometimes very well as well. Sorry. So this one is measuring what type of par? Pardon?
Oh, what type of word?
Yeah. Which ones are planar? Which ones are scalar?
Planar.
Even
Scalar.
Yeah. So. This one I always thought, although they made a bigger version by biospherical, there's a great. Yeah.
So the difference is that planar is then collecting only from one direction, like, and scalar total, from all directions.
Yes, this has a cosine, it's trying to impart it on the surface, right? This is imparting it on the surface over a sphere. So now it's independent of direction. That's the key part of scalar irradiance. It becomes independent of direction.
Are you able to get no, I'm using the wrong terms, but is your overall reading stronger from a planar radiance part sensor versus a scalar radiance?
Why would you think that would be?
Just because you're doing less using them. I'm basing it just off of the diagram that the detector relative to the size of the diffuser looks much smaller.
Are you talking about the response function, or are you talking about which is going to be larger, planar or scalar radiance, like an upward direction?
All right.
Remember,
Yeah.
this whole measurement's being weighted by the cosine, so it has some directionality. This one, we're measuring in all different angles. Which one should be big?
It should be the scalar.
Correct.
Yeah.
the scalar, does it return a measurement for all angles?
No,
Just one measurement?
it's an integrated measurement over all those angles, all that solid angles or integration of all those solid angles.
So why would you want a planar over a scalar?
Various different reasons. These aren't easy to make. They can not be as easy to keep active biofouling. Here you can use paddles, shutter, wipers, things like that on them. These can be, like I said, in this titanium, you can make different components and supporting components to go deeper. These are harder to do because you gotta really thicken up that whole sphere, which is an empty sphere on the inside. By the way, if you look into this on the inside, we done this, I think on Friday, is basically what we call an integrating sphere. Yeah. What we're integrating is the light over all directions. The sphere is just bouncing that light all over the place and then becomes an integrated measurement over all radiance angles.
So scalar irradiance gives you E sub 0.
Correct.
And planar irradiance gives you E sub D and E sub U. But it seems like you need all three to get to that absorption using.
Correct. Correct.
So do people bring all three of these out into the field or?
Not very often. We're gonna get more into configurations tomorrow. So there's different ways, different configurations where you can get at different parts of it depending on your setup, your combination of sensors you do have.
If you have no planar in different directions, is it kind of equal to the scale?
Not necessarily, no. Not necessarily, no, because now you get into shading effects. You're kind of looking at, you're rotating your sphere again. Sun. Right? It's over drag side together. Here's your planar. And the radiance, this is the downwelling, this is the upwelling. What happens if you kind of rotate it this way? Well, I think the sun's over here. I'm looking this way. I'm always going to have a body somewhere, in the scalar or in the planar. Connector now is pointed this way, where in other words, this instrument, in this inversion, is the cosine collector. And now I'm not really shading my measurement. Light's coming here, it's hitting it at some angle. Light's coming off, but I'm really not shading the measurement. It's hitting on that surface. Here, I have the possibility of a little more self-shading it. So doesn't necessarily mainly just because of the setup and you can't make it an infinitesimally small. I think that's it for this presentation. I did want to point out, since I have a little bit of time, if you go to labsphere.com, and search on it, I think it's just called Radiometric Terms and Units, a really good 2-page handout. I keep it with me. It finds all the bandwidths, radiance of the sphere, solid angle approximations, some conversion factors, black body absolute radiance, whole bunch of useful concepts, constants, their values and definitions. And the next page is really awesome too, because everybody measures stuff all throughout the literature, whether you're a biologist or a physicist, the units change. So there's conversion factors that's listed. I have a measurement here, but I want to convert it to this type of measurement. So really good. You can probably look that up on the web. It's quick, but I like to have that little cheat sheet.
I wasn't able to request a laminated version, but eventually I was able to get the PDF.
Oh, good.
Send them out there.
They used to do a laminated version.
Yeah, I couldn't find.
Yeah. So really good handout, but you can get the PDF and print it and wrap it in saran wrap. Laminate.
Doing desktop.
All right, thank you guys. Any questions? Other questions?
I still have the question of what's the data from the hemispherical radiance sensor corrected for self-shading in the graph that you showed?
Which one are you talking about now? This one?
Yeah, this one.
You know, that's a great question.
Is the data for upwelling
I think-
radius?
I think-
Self-shading of the instrument.
Yeah, I think if you think about the self-shading, self-shading, it's worse when, you know, you're right, you're looking
Yeah.
to an up, it's right on this data right above. So typically that's where you try to put it at an angle. So that the shade is, you know, have the sun at an angle, so the shade's falling off to the side. If that makes sense.
But upwelling radiance measurement are usually made at nadir. Right?
We make them at nadir, but
Yeah.
that's again going back, where's the sun really? That's why I was trying to point this out. This isn't really in the center of that sphere.
Yeah.
The sun's at some angle.
So in this context,
We
the
put
sun
it-
would be straight back to the instrument, so the instrument will shade directly the direct sunlight.
If the sun was directly
Yeah,
at the zenith, right above my instrument, you'd get a fully shaded upweld measurement.
Yeah.
But if the sun was at an angle, just like your shadow falls off to the side. So you're still looking at light coming off. Now, there could be still a
There-
shading on the edge.
there
but
is still a volume that is
There
shaded.
is, but it's not as the same as doing it at nadir.
No, but
Yeah.
I think that it still affects this measurement, right?
Yeah, I would assume so too. I've never actually made this measurement before, but
Okay.
hard to get my hands on the fisheye lens system. Okay.
Thank you.
Yeah.